Okay, let's unpack this. This whole concept of the universe, for the longest time, it just meant everything, like the whole cosmic enchilada, right?
That was the definition, absolutely.
Yeah.
Everything there is.
But lately, it feels like the cosmos is expanding conceptually, too. We're starting to hear talk of universes, plural. This is a pretty big shift in
Yeah,
thinking.
it really is. And what's driving it, interestingly, are developments in theoretical physics. We're now seriously considering multiple realms, maybe beyond our ability to ever see. It's not just sci-fi anymore.
Exactly. And to help us navigate this, well, potentially infinite landscape,
Hmm.
we're doing a deep dive into Brian Greene's The Hidden Reality, Parallel Universes, and the Deep Laws of the Cosmos.
Great book. He tackles some really complex physics, but he does have this knack for making it well understandable.
Yeah, he brings in relativity, quantum mechanics, but only as needed, you know, with pointers if you want the really deep technical stuff.
Right. And our goal today isn't to get bogged down in all the equations of those theories.
Yeah, definitely not.
We want to focus on the core ideas of the multiverse that Green presents. Really aim for clarity, something everyone can grasp. Think of it as the highlights tour.
Highlights tour, I like that. And Green kicks things off with what he calls maybe the simplest route to parallel worlds.
Mm-hmm.
It stems from just thinking about space itself.
Yeah.
What if it just keeps going?
Mm-hmm. Infinite space. If you accept that possibility, that space extends forever in all directions.
Then what happens?
Well, then logically, any possible way that matter and energy can be arranged must happen somewhere out there. And not just once, but infinitely many times.
Okay, this is where it starts getting wild. Like, Green uses the Imelda Marcos analogy with her shoes,
Mm-hmm.
or maybe an infinite wardrobe.
Right, or the wardrobe. The point is, she only has a finite number of possible outfits, even if it's a huge number.
So if she has infinite chances and infinite number of days to get dressed, eventually she has to repeat outfits, exactly the same one.
Exactly the same ones, over and over, infinitely often. Or think of Randy the card dealer Green mentions, an infinite number of decks. There's only a finite number of ways to shuffle 52 cards. A massive number, sure, but finite. Shuffle infinitely, and every single order repeats endlessly.
Right. And so Green applies this to cosmology, to the universe.
Mhm.
We have this cosmic horizon, don't we? The edge of what we can see.
That's right. It's basically the distance light has been able to travel to us since the Big Bang. It defines our observable patch of the universe.
But if the whole universe is infinite,
then there must be infinitely many of these patches, these cosmic horizons, completely beyond our own,
yeah.
like countless separate bubbles that have never, ever interacted.
Okay, but hold on. Someone might argue, well, what about tiny, tiny differences? Like, what if one atom is like a nanometer to the left or moving microscopically slower? Aren't there infinite shades of difference possible?
That's a really sharp question. It gets right at the heart of whether these infinite possibilities are truly distinct. And the answer comes from quantum mechanics.
Ah, quantum mechanics, of course.
Specifically, the uncertainty principle. It puts a fundamental limit on how precisely we can know certain pairs of properties, like a particle's exact position and its exact speed at the same time. There's an inherent fuzziness.
So even with perfect instruments, you can't pin everything down with infinite precision.
You can't. And that fundamental fuzziness means that within any given cosmic horizon, any finite volume of space, there's actually a finite number of truly distinguishable arrangements of particles and energy. It's a staggeringly huge number, but it's not infinite.
Okay, let me try and stitch this together.
Yeah.
We've got potentially infinite space overall,
Mm-hmm.
filled with countless bubbles or cosmic horizons. And within each bubble, because of quantum limits, there's only a finite number of ways things can be arranged.
You got it.
So, infinite space, finite possibilities per patch. The patches have to repeat.
Yeah.
Just like the outfits or the card decks.
That's the inescapable conclusion of this line of reasoning. And the really, really mind-bending part is that this implies there must be infinitely many patches out there identical to ours.
Identical, like completely identical.
Down to the arrangement of atoms in you right now, listening to this. Somewhere out there in this level 1 multiverse, there's another you. Infinitely many, in fact.
Whoa. Okay, that's a lot. Let's maybe move on before my brain melts.
Yeah.
Level 2 multiverse. This one comes from inflation, right?
That's right. Inflationary cosmology. We know the universe is expanding now after the Big Bang. Inflation proposes this period of absolutely crazy, super fast expansion that happened in the very, very first fraction of a second.
Like way faster than the expansion we see today.
Oh, exponentially faster. It was proposed to solve some puzzles about the early universe, like why it looks so uniform on large scales, why the cosmic microwave background temperature is so smooth, and why space appears geometrically flat.
And what powered this insane expansion? You mentioned something called the inflated field. Sounds very sci-fi.
It does, doesn't it? But it's a hypothetical quantum field. Think of it as this energy field that permeated all of space right at the beginning. Its key feature was having a uniform energy density and, this is the weird part, negative pressure.
Negative pressure. How does that work? Pressure pushes out.
Usually, yes.
Right.
Positive pressure pushes out. Negative pressure is more like tension within the field itself that causes space to expand. Imagine stretching a rubber band that has tension it wants to pull back. A field with negative pressure, when it fills space, effectively generates repulsive gravity. It pushes space apart.
Okay, repulsive gravity, that's counterintuitive.
It is. Another way to think about it, if you have a box filled with something that has positive pressure, like air, and you make the box bigger, the pressure drops. But with this inflated field, if you make the box of space bigger, the total energy increases because the new space is also filled with this energy density. That behavior is characteristic of negative pressure.
Got it, sort of. So this inflated field drove the expansion. But it had to stop, right? Or we wouldn't be here. How did it switch off in our region?
Green uses an analogy. Imagine the energy state of the field as a ball rolling down a hill, or maybe a potential energy landscape. Inflation happens when the ball is rolling very slowly across a high, flat plateau.
Okay.
Eventually, in our patch of the universe, the ball rolled down into a valley, a lower energy state. As it rolled down, its energy was converted into the particles and radiation we associate with the hot Big Bang. That transition ended the inflationary period locally.
Oh, how does that lead to multiple universes if it just ended here?
Well, quantum mechanics again. Even as this field was rolling, there were tiny, unavoidable quantum fluctuations, little jitters happening everywhere.
Like ripples on the surface?
Sort of, and these quantum jitters meant that different regions of space didn't finish rolling down the hill at exactly the same time. Some patches dropped into the low energy state, ending inflation there.
While other patches maybe kept inflating.
Precisely. Inflation stopped here, creating our observable universe. But elsewhere, it could have continued. And in other regions, it might have stopped slightly later, or maybe even earlier under slightly different conditions. This creates a vast cosmic structure where inflating regions spawn off bubble universes where inflation has ended.
So we're living in one bubble that popped on from a still inflating background.
That's the picture of the level 2 multiverse. And crucially, each of these bubble universes could itself be spatially infinite.
Oh, wow. So each bubble could contain its own infinite set of level 1 parallel worlds. It's like infinities nested within infinities.
Exactly. It's a staggering concept. And furthermore, the way inflation ended in each bubble could be slightly different. The specific value the inflating field, or maybe other fields like the Higgs field, settled into, could vary from bubble to bubble. Meaning the fundamental constants of nature, things like particle masses, force strengths, could be different in other bubble universes. The basic laws might be the same, but the parameters governing how those laws play out could be wildly different. You could have universes where chemistry is impossible, or stars can't form.
Okay. My bubble is definitely feeling a bit stretched now. Let's try level 3. String theory landscapes. String theory. That's the one where everything is made of tiny vibrating strings instead of point particles aiming to unify all the forces.
That's the core idea, yes. Trying to be a theory of everything, unifying gravity with quantum mechanics. And one of the most striking requirements of string theory, for mathematical consistency, is the existence of extraspatial dimensions.
More dimensions than our usual 3, length, width, height, plus more. Where are they?
Well, the idea, going back to earlier theories like Kaluza-Klein, is that these extra dimensions could be curled up incredibly small. Think of a garden hose. From far away, it looks one-dimensional, just a line. But get close, like an ant walking on it, and you realize there's a second dimension, the circumference, that's curled up. String theory suggests maybe there are 6 or 7 extra spatial dimensions, but they're curled up on scales far too small for us to perceive directly.
Tiny curled up dimensions everywhere. Okay. How does that make a multiverse?
There are a couple of ways proposed. One is the Brane world scenario. Brane is short for membrane.
Right.
Imagine our entire three-dimensional universe isn't the whole show, but just a three-dimensional brane, like a sheet, or Green uses the analogy of a slice of bread.
A slice of bread in a cosmic loaf.
Exactly. floating in a higher dimensional space, often called the bulk.
So there could be other slices, other 3D universes parallel to ours in this bulk.
That's one possibility. They could just exist side by side. Another, more dynamic version suggests these branes might move in the bulk and could even collide.
Colliding universes, what would that do?
Some theories propose that a collision between branes could trigger a Big Bang event on the branes themselves. This leads to ideas of cyclic universes, where Big Bangs happen repeatedly as branes collide, separate, and collide again. Parallel universes in time, in a sense.
Wow. Okay. Brains. But what about the landscape part?
The landscape comes from those extra dimensions. They aren't just simple circles like the garden hose. According to the theory, they can be curled up into incredibly complex, multi-dimensional shapes called Calabi-Yau manifolds.
Talabia.
And here's the kicker. Mathematicians and physicists have found that there isn't just one way to curl up these extra dimensions. There's an absolutely astronomical number of possibilities for the shapes and sizes of these curled up dimensions.
How many?
The estimates are mind-boggling. Something like 10 to the power of 500 different possibilities.
And with 500 zeros after it. I can't even picture that number.
Nobody really can. It's vast beyond comprehension, and each distinct shape, potentially combined with different ways energy fields called fluxes, can wrap around these dimensions. Could correspond to a universe with different fundamental constants, and maybe even different fundamental particles and forces. It creates this vast landscape of possible physics.
So connect that back to the bubble universes from inflation.
Well, the idea is that perhaps each bubble universe that forms in the level 2 inflationary multiverse lands somewhere different in this vast string theory landscape. Each bubble realizes one of these 100-500 possibilities, resulting in an enormous collection of universes with potentially every conceivable variation in the laws of physics.
And Green mentions this might help explain the cosmological constant, that weird dark energy accelerating the universe's expansion.
It offers a potential framework, yes. If there are countless universes with different values for this constant, maybe we just happen to live in one where the value is small and positive, allowing structures like galaxies and us to form. It's called the anthropic argument, though it's debated.
Right, okay. Deep breath. Level 4. The quantum multiverse. The many worlds interpretation. You said earlier this one feels different.
It really does. It's not about infinite space or extra dimensions or cosmic bubbles. It emerges directly from the weirdness of quantum mechanics itself. You know how quantum mechanics describes particles not with definite properties, but with probability waves?
Yeah, Schrödinger's equation tells you the probabilities, like an electron might be 50% likely to be here, 50% likely to be there.
Until you measure it.
Exactly, until you measure it. And in the standard way of thinking, the Copernican interpretation, the act of measurement somehow forces the particle to choose one state,
Right.
and the probability wave collapses.
It becomes definite.
But the many worlds interpretation, proposed by Hugh Everett back in the 50s, asks, what if the wave never collapses?
Never collapses. What happens then?
Then every time a quantum measurement occurs, or any interaction that could distinguish between possibilities, the entire universe branches. It splits into multiple parallel copies.
Yeah. So if the electron could be spin up or spin down, the universe splits into two distinct universes. In one, the electron is spin up, and a version of you sees that. In the other, completely separate universe, the electron is spin down, and another version of you sees that.
So every quantum choice, every possibility encoded in the wave function actually happens, just in a separate world.
That's the core idea of MWI. All possibilities are realized in their own branch of reality. Green uses this fun analogy of a Zaxterian cloning machine.
Okay.
Imagine it makes perfect copies, but maybe there's a random coin flip that determines the eye color of the clone. After it runs, you have multiple copies, each experiencing a different outcome, but from the perspective of each copy, it just seems like a random event occurred. MWI suggests quantum measurements are like that, constantly splitting reality.
If these splits are happening constantly for every quantum event everywhere, why don't we perceive these other worlds? Why don't I bump into my other selves making different choices?
That's the crucial question, and the answer lies in a phenomenon called decoherence.
Decoherence.
Essentially, for large, complex systems like us and our measuring devices, the different branches of the quantum wave function become entangled with their environments in incredibly complex ways. This entanglement effectively isolates the branches from each other. They can no longer interfere.
So they become separate, independent realities.
For all practical purposes, yes. They decohere, losing the ability to interact or influence each other. So while the branching might be happening constantly at the micro level, the resulting worlds become invisible and inaccessible to one another almost instantly.
Still feels pretty wild, but the cloning analogy helps a bit.
Yeah.
Okay, one last level of weirdness.
Yeah.
Level 5, the holographic principle. This one sounds the most like something out of, well, The Matrix or something.
It is perhaps the most radical and counterintuitive of the bunch, but it stems from deep thinking about gravity, black holes, and information. The basic idea is that all the information contained within a volume of space
Yeah.
might actually be fully described by physics happening on the boundary surface of that region, like a hologram.
A 3D reality encoded on a 2D surface.
Huh.
How did anyone even come up with that?
It emerged partly from studying black holes. Physicists like Bekenstein and Hawking discovered that the entropy of a black hole, basically, a measure of its information content or disorder, isn't proportional to its volume, as you might expect.
No. What's it proportional to?
Its surface area, the area of its event horizon. This was a huge clue. It suggested that the maximum amount of information you can possibly cram into a region of space is determined not by its volume, but by its boundary area.
Whoa. So the 3D information is somehow limited by or maybe encoded on the 2D boundary, just like a hologram stores a 3D image on a 2D piece of film.
That's the analogy precisely. And it went from a conjecture to something much more concrete with the work of physicist Juan Maldacena in the late 90s, using string theory and branes.
Brains again.
Yes, he found a specific mathematical example, a duality showing an exact equivalence between a theory of gravity happening within a certain volume of spacetime and a quantum field theory, without gravity, living on the boundary of that spacetime.
An exact mathematical match.
A precise dictionary mapping concepts in one theory to concepts in the other. It strongly suggests that, at some fundamental level, a reality with gravity in a certain number of dimensions can be equivalent to a reality without gravity in one fewer dimension, living on its edge.
So, our entire three-dimensional universe could potentially be just a projection, a holographic image generated by information on some distant, vast, two-dimensional surface.
That is the absolutely mind-bending implication of the holographic principle. Our familiar 3D reality might be an emergent phenomenon, arising from a fundamentally 2D description located on the universe's boundary.
Okay, I think my definition of reality has officially been, well, holographically smeared. We've gone from infinite copies in infinite space to bubble universes, brain worlds, splitting quantum realities, and now maybe we're just a projection.
It's quite a journey through theoretical physics. And it's just so crucial to keep in mind these are all theoretical frameworks. They represent our best efforts pushing the boundaries of math and physics to understand the ultimate nature of the cosmos based on the laws as we currently understand them.
Which brings up that big question, doesn't it? If these other universes are fundamentally unobservable, maybe forever beyond our reach, is this even science? Can you scientifically talk about things you can't see or test?
That's a very fair and important question. It's a point of debate, even among physicists. But as Green points out, the justification often comes indirectly. If a theory that predicts a multiverse also makes successful, testable predictions about things within our own observable universe.
Like if string theory eventually predicted the correct particle masses, maybe.
Exactly. Or if inflation correctly explains details in the cosmic microwave background radiation, then the success of the theory in the observable realm can lend some credibility to its entire structure, including the parts we can't directly observe. It becomes part of the underlying architecture that seems to work.
So it's about the explanatory power of the whole framework. Okay. So wrapping this up, what's the big takeaway? What should you, listening right now, really ponder after this deep dive into Green's hidden reality?
I think maybe the most profound thing is how these ideas challenge our bedrock assumptions about reality itself. What is real? What are the limits of our perception, our intuition? Could this seemingly solid three-dimensional world we inhabit be just one facet of a vastly larger, stranger, and maybe infinitely more varied reality that remains hidden from us?
A hidden reality. It's definitely something to think about. Leaves you wondering what else might be out there.